Okay, so, oh gosh, wait, it just switches on me all of a sudden, doesn't it? Okay. All right, so here's where we were. Last time we were talking about vectors, and recall a vector is it's a little mathematical construction we've created. It's a pair of things. It's a direction paired with a magnitude. Which seems like an odd pairing until you notice that it's exactly what we need to describe certain things like displacements, velocities, forces. We're going to find other things as well that are perfectly described by a combination of a direction and a magnitude. So vector is a very natural construction, as it turns out. There is a correspondence between points, locations in other words, and vectors. Remember, we represent vectors by arrows of certain direction and magnitude. Right? There's a perfect correspondence between points and vectors, and that goes by way of putting the tail at the origin. In other words, putting the vector in standard position. So for any given point, there is exactly one arrow whose tail starts at the origin and whose head is at that given point. Namely, for any given point, there is exactly one corresponding vector, which of course can be represented by lots of different arrows. But anyway, for every point, there's exactly one vector and vice versa. Okay, so we talked about that last time. Okay. Okay. So just a quick reminder, vectors have direction and length, but they don't have location. Points have locations, but they don't have direction or length. Right, so they're kind of complementary. It's a weird thing that they're perfectly paired with each other, and yet they have sort of complementary features. That's kind of weird. So along those lines, I want to look at this picture and talk about, how would you describe the occurrence that now I'm sure you've noticed, the relationship between this line and this vector, and the strong urge looking at this situation is to say that vector is in the line. And you have to resist this temptation to want to say it that way. It's extremely misleading and really downright inaccurate to say that this vector is in the line. And let me explain why. When you're talking about points and vectors, right? Keep in mind they have these complementary features. Points have locations, vectors don't. So if you say V is in the line, okay, well, V, what is this V thing? He said in the line. He's referring to the location of V. Location. Oh, well, vectors don't have location. Points have locations. We must be referring to the location of the point that is associated to V. And that point, by looking at, keep in mind there's all these different arrows that equivalently represent the same vector. There's only one such arrow that's in standard position. The point associated to V is that one, that red point. And that red point is very clearly not in the line L. Right, so if you say V is in the line, that's just not true. Right? Here's another way to say it. If you say V is in the line, on the basis of the fact that this arrow representing it is in the line, okay, well, what about this arrow just as well representing V that is obviously not in the line, or all these arrows over here that are very clearly not in the line? That's not really... The word in is not a good description of the relationship that V and L have. Now, of course, clearly there's a relationship here. There's something going on. So how do we get our hands on what is it that these have in common? And I propose that a very reasonable choice is that they are parallel. Right? And that's really the point, right? I mean, it's the fact that the direction of V is the same as, if you will, the direction of the line. That's really what we're trying to describe. So say parallel, and you got a heads up on this, because again, you see this picture, and it's super tempting to say V is in the line. but it's better to say parallel to the line. So again, just for comparison purposes, this is what it would mean to say V is in a line. Right? This vector, as soon as you say in, you're talking about location. That means you're talking about the corresponding point, and that corresponding point is in or on, as you prefer, the line. Okay, all right, enough of that. Okay, so a little bit of algebra of vectors. Let's talk about magnitudes. If we have a vector in R2, here's a vector in R2, how would I describe the magnitude of the vector? Well, magnitude is represented by the length of the arrow. That was our rule, right? We decided to use arrows to represent vectors because arrows point in directions, and by way of their length, they have a sort of implicit magnitude. So we're choosing to draw arrows whose length is the magnitude. Well, that length is a distance. It is a hypotenuse of a right triangle, and we have a very handy-dandy formula for computing hypotenuses of right triangles. So the Pythagorean formula computes, in addition to hypotenusi, right, it computes magnitudes of vectors. Okay. Handy. Note the notation that we're using here to represent the magnitude of a vector, double bars. It's standard notation. Here's an exercise. Suppose you have a vector in R3. So a vector with 3 coordinates. It's going to turn out that this is the formula for the magnitude. But that's a more significant geometry problem. I'm going to leave this as an exercise for you guys to work out on your own. By the way, I'm going to do this kind of thing a lot. I'm going to leave a lot of calculations as exercises. So 2 things. First of all, that means that I think it's a good use of your time. It's something you should be able to do. It'd be a good measure of whether you're kind of keeping up with the ideas. Are you really following along? And the other thing is, I'll point out that this decision-making process that I have of what to leave as an exercise for you guys, it's not that different from my decision-making process of writing exams, and it has happened kind of coincidentally on more than one occasion that I have made an exam question because I thought, this is something I think they should be capable of. It's interesting and kind of also a little learning experience. This would make a great exam question, and then it turns out that I'd forgotten that I had left that as an exercise in class for exactly the same reasons. So coincidentally, it turns out that what I say, this is an exercise for y'all to do on your own. If only you're motivated by preparing for the exams, not a bad idea. So give this a try. By the way, another thing about exercises that I leave for you to do on your own in situations like this. Of course, I'm very happy to help you if you get stuck. Right, come to office hours, work it out. Show you what I wanted you to do. Ditto the help room. By the way, the help room is not yet open, but it's going to start probably tomorrow. Anyway, once it's open, I'll let y'all know what the hours are. It'll be posted on the web page, and I encourage you to make big use of the help room. It's going to be something like 4 hours a day, probably in the afternoons. That it'll be open, and there will be a grad student in there ready to answer whatever questions you might have. Okay. Alrighty. So, I'll mention as well, there's another notation for magnitude of a vector, and that is to use single bars instead of double bars, to which you might complain, wait a minute, that means absolute value. Isn't that different? And if you think about it, it's actually not. You can interpret magnitude of a vector as kind of a generalization, really, of the idea of absolute value. Imagine a one-dimensional vector. What would that mean? One-dimensional vector. Well, it'd be a vector on the real number line. It would be represented by a single coordinate. In other words, it's a number, right? And if you think about it, magnitude in the sense of how long means the exact same as distance from the origin means the exact same as absolute value, right? So it's a very reasonable notation, in fact, to use single bars instead of double bars. I still like the double bars. when I took this class the first time, when I was y'all's age-ish. They use double bars. I kind of like the fact that it's a cosmetic reminder that we're talking about a feature of a vector here. So, I don't know, I kind of like it for that reason. But you are welcome to use single bars instead if you'd like. Anyway, the book is going to use double bars. You're welcome to do whichever you like. Okay, more algebra. Let's talk about addition. How do you add vectors? There is a first thought that I want y'all to have to the question, how do you add vectors? First thought should be, you know what? I don't know. Now, I pose this as a non-trivial thought because there's a temptation to think, hey, addition, I learned addition in elementary school. Come on, I'm an expert on addition. I know how to add stuff. Right? We'll slow down. You know how to add real numbers. Right? So we've got here now a completely new thing. We've got this idea of a vector. That is not a real number. And it is not yet defined. I mean, we have not yet defined what it should mean to add two vectors any more than we've defined what it should mean to add two cars. Right? Do you know how to add cars? No, of course not. So what we have here is a uncharted territory situation, right? So the notion of addition is familiar, but it's familiar only in a single context. We are in a different context. Okay, so keep that in mind. So next question, what should it mean? Right? What definition should we write down? Let me take it a little bit more general than that. What should my process be? What should I be looking for in coming up with, an idea for how to define addition for vectors? One motivation you could take is, well, I want to make a definition that looks good on the page. I want something that's algebraically easy to work with. Right? Seems like a natural motivation. I want to caution you against this as a motivation. Writing down formulas that are easy to work with. Here is an example. I had that idea once when I was very young. I think I was in like first grade or whenever it is that you learn how to multiply. And I was very frustrated at the fact that, 4 times 7 was 28. Weird. You're telling me I have to memorize like 100? I have to this whole multiplication table. I got to memorize the whole thing. Look, this is a lot of trouble. Why don't we just agree that 4 times 7 is 47, and then let's call it a day, right? I mean, this is much easier. It's much more efficient, right? Algebraically, extremely appealing. You see what I'm saying? Okay. And meaningless. Right? This serves no purpose. What do you do with this thing? What does this have to do with stuff I actually care about? Nothing. Right? Okay. So, the idea of multiplication, of course, y'all know this, but the point is, that's 4, that's 7. Multiplication is a way of counting, how much area is there in the corresponding rectangle. So that's geometrically natural. Is the point, right? So when we go to the trouble of writing down and memorizing multiplication tables, it's not just to be annoying. It's because that's a way of having an operation that means something, right? Geometrically. You can have definitions that mean things physically, right? But there should be some sort of a natural application of your operation when you write it down. So we find ourselves here again, how should we define addition of two vectors? And I urge you, don't fall for it'd be really tempting to want to write down something like this, like if you have a vector v1, v2, and you want to add a vector w1, w2. I mean, the hope, the algebraic, the version of what I came up with as a 7th grade, 7-year-old or however old I was, would have been, here's the naive hope, V1 plus W1, V2 plus W2. That'd be very convenient algebraically, but it's not at all clear that this means anything at all geometrically. Everybody on board with the concern? Okay. So let's not just write stuff down because it looks useful, because it looks convenient. Okay, so here's what I propose would be a reasonable a reasonable definition, easy to motivate. And this comes from the idea of what vectors represent. And I want to represent vectors, think of vectors as representing displacements. That was our first sort of, concept of, why did we come up with this notion of a vector in the first place? And so I propose that if you have the notion of displacing, the notion of displacing in that direction by that distance, and then subsequently you want to displace in that direction by that distance, well, let's just follow those instructions. First displacing as V indicates, and then having done that, from that, stopping point, now displace as W instructs, that direction by that distance. Grand total, you might say, altogether, you started here, you ended there, and therefore in total you have displaced by that purple vector. And that seems like a pretty reasonable choice to me of what to call the sum of those two vectors. Everybody see how that's geometrically natural? I mean, this is fundamentally connected to the interpretation, our fundamental interpretation of what vectors are. Very geometrically natural. It's going to turn out as well to be physically natural. Okay. All right, so here's the really good news. And that is that having motivated a definition based on this natural geometric interpretation of vectors, it turns out that the algebraic formula is exactly this. All right, so it's a happy ending. Now, I like to present this in the way that I have, as I like to discount this first, because if you just write this down, it's like you're endorsing writing down formulas pulled out of nowhere, motivated simply by laziness, right? And I don't want to encourage that kind of thinking, right? So I like to trash talk this first as being, oh, come on, that's naive, that's childish. This is natural and thoughtful, and then convenient. What a stroke of good luck. Turns out this was right after all. Okay, so all right, so let's move along. Next question: what should it mean to multiply a vector times a scalar? So if you have a vector here, let's think of it as representing a displacement. If someone says move that way by that distance, and then someone else says, yeah, no, same thing, but c times as much. Well, he's moving the same direction by c times that distance, right? Seems like a very reasonable choice. To define vector times a scalar by that picture. And then similar triangles arguments make it easy to motivate this formula here. So again, I'm going to leave that as an exercise. This and the previous one. Right? Confirm that the geometric motivation pictures that we wrote down, confirm that these two pictures motivate the two formulas that I've claimed. It's just a matter of writing down the pictures and thinking about the coordinates and et cetera. Okay, now a little bit of an ugliness comes up when you consider the possibility of, well, wait a second, what if this scalar is negative? Does that weird things up a little bit? If you look at the this formula and think about, well, what does this formula do when c is negative? What it does, awkwardly, is it takes a vector, let's say, pointing that direction, and the resulting product if you just write down the coordinates, ends up pointing the exact opposite direction. And is that weird? Is that unsatisfying physically? No, in fact, that's kind of perfect if you think about it. A negative means a kind of an opposite. So as it turns out, the way that opposite manifests itself in having chosen this formula is that it changes the direction to the opposite direction. So perfect. Couldn't ask for a better result there. Okay. this is going to be a homework exercise. In fact, I think this is actually one of the book homework exercises to confirm this formula. Not too shocking at a glance, right? C times V is C times V is the way a lot of people would read that. Of course, it's not what this says. This says that if you take a vector V and multiply it by a scalar and then take the magnitude, that's the same as first taking the magnitude and then multiplying. You're going to want to say multiplying by the scalar, but it's not. It's multiplying by the absolute value of the scalar. So you take a deeper look at this formula, and there's a little bit of an eyebrow raised there. Why shouldn't this formula be, that? A lot of people would say that's what it ought to be. But it's not. I mean, if you think about it, this fails the sanity check in the sense that we know that this will always be positive, and we know that that will always be positive. So we can't have a formula that says positive equals positive times possibly negative. That's not okay, right? So taking away the absolute values would fail the sanity test. Everybody see what I'm talking about there? Okay. Now that alone is not a justification for you sticking in absolute values. If you have a false formula that has an obvious contradiction in it, just sticking something in there to remove that contradiction does not automatically make it true, right? It makes it not have that obvious failure, but it might have other failures. So it's not immediately obvious that this is true. So I want you all to prove this formula. It's a straightforward calculation. You have sorry, I forgot to change the color. We have an explicit formula for how to multiply C times V. You can write that down algebraically, exactly what that formula is. You have an explicit formula for what it means to take the magnitude of a vector. Write it down. Right? And you write down exactly the formulas for all that stuff and plug and chug. Right? And I claim that this is what you're going to get. You're going to end up with exactly the formula for the magnitude of the vector V, and this little absolute value is going to show up. Now, how that absolute value comes about is a result of a true fact that is very often swept under the rug in high school algebra classes. So I'm going to point this out to you. A lot of students misunderstand how square roots work. Certain subtleties in I don't know, middle school or whenever this gets brought up are many schools feel like, well, it's best to just sweep the subtleties under the rug. Let's get students comfortable with the basics first, and then they kind of never come back to it. So a lot of people think that square roots undo squares. It's not really true. That's true sometimes, right? But it's not true in general. So specifically, this symbol here, a lot of students that think that means, the square root. That's how we say it, right? Most of the time we'll read square root there. But every non-zero positive real number has two square roots. That does not mean pick one. It does not mean both. That symbol means the positive square root. It means positive. That's the rule. Okay, so notice then the square root of the square. Now you're tempted to say, oh, well, then whatever you put inside the parentheses there, I mean, you're squaring, you're undoing the square, it's going to be the exact same thing. But it's not. You put a -3 in there, you get square root of 9, that is 3. It's not -3. Everybody see what I'm talking about? So, I mean, it's one of these, why are we talking about middle school stuff? I learned that a long time ago. Yeah, and you may, or you very likely, in my experience, your teachers might have kind of failed to mention this. So here's the general fact about the relationship between squares and square roots is this, and that is the square root of the square of a number is the absolute value of that number. Real numbers. Okay, so anyway, this is, you got to make sure to be thoughtful and careful about this particular aspect of algebra when you're going through and trying to prove this formula, and that's where the absolute values come up in that calculation. So the rest of the details are for you guys. Okay, moving along. How do you subtract vectors? Well, turns out we don't get to make a choice on this. This is a definition that we have inadvertently already chosen because we've already defined what it means to add two vectors, and we've already defined what it means to multiply a vector times a scalar. So since we've already decided on what that means, and we've already decided on what that means, well, then we've already decided on what that means. So we just have to go through the rules, and it turns out that you get this picture with vector subtraction. It's pretty easy to motivate. I'll tell you the way I think of it. I think that the most convenient way to think of it is that v minus w is, and really better be, the thing that you add to w, right, to get v. I mean, how much trouble would we be in if v minus w plus w wasn't v? I mean, we wouldn't be able to do any algebra at all, right? So that's the picture that I draw in my mind. There's different ways to think about it, but anyway, that's the way I think about it. Any questions about that? Everybody happy? Okay. All right. Okay. Here's some algebraic facts about the operations that we've just defined. We've defined vector addition. We've defined scalar vector multiplication. Now, again, it's tempting to, yawn when you see these properties, and yeah, okay, sure, it's a little boring, right? But one of the reasons that we like to have algebraic operations is so that we can do algebra. And when you do algebra, what you're doing is you're putting into effect algebraic properties, right? So one of the big strategies in math is to take geometric things, or physical, geometric, things that we want to understand better for sort of immediate reasons, translate into the world of algebra, and then do algebra, right? So what algebra am I allowed to do is critically important in being able to to address the matter of what questions can I answer about these objects that I'm interested in. So anyway, here's some facts about algebra that we are allowed to work with. Again, there's temptation to say, come on, I learned these in elementary school. I thought it was annoying in 5th grade when they made me memorize that this was called the commutative property of addition. I was like, wow, that's a big word for a perfectly obvious concept, right? Well, the reason we give it a big name is because the addition that we learn in, I don't know, 1st grade, 7th grade, I forget when it is. That addition is just one of many kinds of addition that mathematicians use. So we add numbers, we also add vectors, we add matrices, we add functions, we add linear transformations, a long list of things that we add in different contexts. And then there's other kinds of operations that we use that are being different things. Math is full of operations. Some of them are commutative and some of them are not, right? So it's a lot easier to talk about which operations are commutative as opposed to which operations have the feature that if you add them in the opposite order, you get the exact same value. Right? So it turns out to be a very convenient thing to talk about. Whether it needs to be introduced in 5th grade, reasonable question. Right? But anyway, so this brand new addition that we've just defined, that you've never seen before, because it's an addition of vectors that until yesterday you very likely had never seen before. This brand new operation, which need not have algebraic properties just because I use a certain symbol to represent it, right, is commutative. All right, so that's good news. Likewise, all of these are good news. Okay, it turns out that there's a really important idea that we're going to need to make reference to regularly. That is a unit vector. It's a simple idea. A vector is a unit vector if its magnitude is 1. Some examples of unit vectors. These vectors here, 1, 0, 0, 1. We call these standard basis vectors in R2, by the way. Why we call them standard basis vectors is really a kind of a topic for Math 216. But just out of academic curiosity, how many of y'all are going to be in Math 216 in the fall? Oh, not very many, just a few. Okay, all right. Well, those of you who are going to see me in Math 216 in the fall, I'll give you a discussion on why we call these standard basis vectors. Here in Math 212, we're just going to use the term because that is the term. But so make sure to remember this term, standard basis vectors. These vectors refer, this name, standard basis vectors, refers to vectors like those in R2, these in R3, whose coordinates are all zeros, except for a single 1 in one of the coordinates. If you think about it, these are vectors that point, these are unit vectors that point exactly along coordinate axes. Right? So it ended up being really, really useful. Here's the notation that I like to represent them. The standard basis vectors in R2, we call them E1 and E2. Standard basis vectors in R3, E1, E2, E3. I bet you can guess what we would call the standard basis vectors in R7. It's exactly what you would think. E1, 2, 3, 4, 5, 6, 7. Some books instead will refer to, let's see here. Let me zoom. Some books will refer to these as I hat, J hat, and K hat. IJK, because, I don't know, I guess they figure those are convenient letters to use, and they're arguably more easily distinguished from each other than E1, E2, E3. So anyway, it's a common choice. The reason I don't like that choice is because, you know, I think it's good for y'all to be familiar with that which will make it easier to apply these ideas in R7, right? And if you're in R7, it's a bummer to have to call them IJKLMNO. And if you're at some point in R29, right? And not that weird, by the way, right? There's lots of variables that are involved. The real world's complicated. It's full of lots of different variables. And, you know, you run out of letters. You start using Greek letters and Russian letters. You know, it gets weird. So E1 through E29, very convenient, very simple, natural. There's no end to the convenience of this, whereas there's a finite convenience to that. So anyway, okay, alrighty. Last thing in this section before we go on is turns out that there's a really convenient formula for how to accomplish a certain task that we end up needing to do a lot. And we're going to see this just throughout this course. That is, given a vector, sometimes you want to find the unit vector that points in the exact same direction. And here's the formula that does it. If you have some vector v, just divide it by its own magnitude. And the result is a unit vector pointing in the exact same direction, which is easily confirmed, by the way. If I want to take this vector u, there's u, right? If I claim that that's a unit vector, I'm going to confirm that it's a unit vector by taking its magnitude. I'm just taking the magnitude of this thing that I claim is a unit vector. This is a scalar. So using the formula that I just assigned as a exercise for you guys, if you have a scalar inside of a magnitude, you can factor out the absolute value of that scalar. And of course, that's positive. Therefore, that's positive. Therefore, its absolute value is itself. And then those cancel, and we're left with 1 as desired. So u is a unit vector. Yeah? Everybody good? All right. Okay. All right, so by the way, we finished our first section. Well, technically we finished 1.1 last time, but 1.2 actually has exercises. So this is the first section we finished with exercises. These will be due on, let's see, today's Tuesday, Wednesday's a holiday, so they'll be due Friday. Right? I think I said so much in the email yesterday. Did everybody get the email I sent yesterday, except for our new student? Okay. All right, and I'm hoping with optimism that we'll finish this section as well and possibly even get a good way into the section 1.4. We'll see what happens here. So we're going to talk about products, dot product. How do you multiply vectors? Well, now we talked about what it means to add vectors. Came with a satisfactory answer there. What it means to multiply, but what it means to multiply a vector by a scalar. Right? Because that was kind of easy to motivate, easy to write down. So now I want to address the harder question of what should it mean to multiply a vector times another vector. So again, we find ourselves saying, okay, well, what should it mean to multiply a displacement by another displacement? And we find ourselves falling short of, what physical concept does that remind me of? Multiplying a displacement times another displacement. It's hard to come up with a physical motivation or a geometric motivation. So it turns out, not only is there an answer that is geometrically natural, it turns out that there are two answers that are ultimately geometrically natural. So that's why we have to give this a refined name. We can't just call this a product. We have to specifically call this a certain kind of product. You can't just say multiply two vectors. You got to make sure to make an effort on this. Don't just say v times w. That does not mean anything. Right? We have to talk about which of the two timeses. One of them is going to be called the dot product, which we're going to denote with, as you might suspect, a dot, which you recall is a familiar way to represent a product. And the other one's going to be called the cross product. We'll talk about the cross product later, but it's going to be written like, like a little times, which is another familiar notation to represent multiplication. Anyway, these are not the same thing. This is a totally different concept. We'll talk about it later, possibly later today. For the moment, we're going to focus on the dot product. I'm not going to start with the physical motivation because it turns out to be awkward to do it that way, but there will be a geometric and also a physical, but we're going to focus on the geometric naturality of this formula. And here's the formula. The first thing I'd like to mention about this formula is it does not look very natural. Right? The idea that we would take the coordinates of the v vector and sort of pairwise multiply them by the coordinates of the w vector and then add those products seems arbitrary and kind of out of left field, right? So I hope you're unsatisfied with this formula right now. I owe you some satisfaction on, I claim that this is geometrically natural. It certainly doesn't look it, right? So I owe you some discussion of why it is I claim this is geometrically natural. And we'll get to it. It takes a few minutes. But let me point out something else that's unnatural about this. Notice that a vector dot product with another vector does not give you a vector. Right? When you add a number and a number, you get a number. When you add a vector and a vector, you get a vector. When you multiply a number times a number, you get a number. When you multiply a matrix times a matrix, you get a matrix. We're kind of accustomed to staying within the same little world that we're doing the operation in, and this doesn't do it. Here, a vector dot a vector gives you a number. And make sure to be clear about this. This is not V1W1, comma, V2W2, comma, V3W3. That is not what it is. Those are pluses. This is a single real number computed with a formula that happens to have three terms in it. But it's a single formula that gives you a single number as a result. Okay, that's weird. Okay. All right, now that I've written down a weird and mysterious formula, I owe you satisfaction of, why is this not insane? The first offering I have is that, well, here's some nice algebraic properties that it satisfies. The dot product does. You might say play nice with vector addition in the sense that there's a distributive property. I mean, this thing right, this thing right here kind of looks like a distributive property. This looks kind of sort of like an associative property. This is the commutative property. So it's got some nice algebraic properties. It's worth something. Not too impressive. Let me point out that had I defined this differently, had I defined dot product as just that and scratched off these terms, all three of these properties would still be satisfied. And I'm going to ask you to take my word for it. This is not geometrically natural at all. There's nothing geometrically cool about that. Right? And yet it satisfies these properties. So, don't be too impressed with the fact that this satisfies those properties. At the same time, we do want to be able to do algebra. So it's nice that we have these properties. It's just not impressive. Okay, here's my next offering. If you take a dot product of a vector with itself, you get the give me 2 seconds. You get the magnitude squared of that vector. Yeah, what's up?
So going back to that property back up there.
Yep.
With the scalar times.
Yep.
Two vectors.
Yep.
So it equals the scalar times the first v vector, but can you also have it so that?
Yeah, you can do it the other way. Yeah, no, that's a great question. So you're wondering if I can sort of, instead of sticking this on the, here, let me use a pen. Instead of sticking this on the first vector, can I instead stick it onto the second vector? Yeah. And the answer is yes. And the reason why is you could take advantage of the fact that this is commutative. You could kind of take the v dot w, switch the order, then follow this property, and then switch it back. Yeah. No, that's a great question. Absolutely. Yep. So mathematicians tend to write down the most bare bones minimal set of equations that give us the abilities that we actually really need. But it is important to know that day in and day out that you can do it either way. Yep. Great question. Okay. Okay, so now why should you care about this one? Well, this one is I don't know about impressive, but this is an eyebrow raiser. This is a connection to geometry. Right? Here's our dot product on the left, and here is an unquestionably geometric concept on the right of magnitude of the vector. I mean, okay, wow, well that's something. Now, let me argue against it. It's very narrow. This is only a true statement in regards to a vector dotted with itself. How often are you dotting a vector with itself? Well, sometimes, but I mean, this is not about all dot products. A very narrow assertion. Nevertheless, it is a geometric connection for this formula. So, okay. That's something. By the way, this is going to end up being a very useful formula. This is another formula we're going to be using a lot throughout this course. So make sure to remember that when you dot a vector with itself, you get the magnitude squared. Okay. Here's the next one. This is called the Koshi-Schwarz inequality. This is significantly more interesting than the last one. This refers to any dot product. Any two vectors in Rn. Well, we're only going to talk about this in R3, but anyway. The dot product of any vector with any other vector has this property. And again, it is geometrically natural because, again, the right-hand side is purely algebraic, purely geometric objects, namely magnitudes. Okay. On the other hand, it's got a certain amount of sloppiness in it, right? This does not say equals. The dot product is not exactly a geometric thing. This just says the dot product is in a very sloppy way, with a lot of wiggle room in it, related to something that's geometrically natural. So, by the way, just a little bit of a heads up. Why do we give this a name if it's not that impressive? And we are going to write down a formula in a moment that is more sort of impressive in the Math 212 context. This is not the big one in the context of Math 212, but arguably in other contexts this really is the big one. And just a little, this is kind of a little cultural note, but it turns out that the dot product is just one example of a more general kind of construction called an inner product. Inner products are crazy powerful. Ultimately, image compression, a lot of the ideas in image compression come from inner products. Netflix works because of inner products. This is a really big deal, right? And the dot product is the first example, sort of the easiest example of an inner product. What's amazing about the Cauchy-Schwarz inequality is that it is not only true just for the dot product. This statement, the Cauchy-Schwarz inequality, is true for all inner products. So it's a fundamental fact about linear algebra. In Math 216, we'll talk about this in more detail. But it's a fundamental fact about linear algebra in an aspect of linear algebra that is, again, crazy powerful. Okay, so it's a big deal fact and very worthy of having a name. Okay. All right, moving along. Here's what I'm going to say, in the context of Math 212 is the big one. And that is that the dot product satisfies this formula. This is any dot product in R3. We'll say R3. So any two vectors. Equals, none of this sloppy inequality nonsense. Equals. And then everything on the right-hand side is geometrically natural, right? Magnitude and magnitude, it's fundamentally geometric, right? Angle. I mean, it's a very fundamentally geometric concept, right? So everything on the right is geometric. So, I mean, you could almost read this equation as saying the dot product really is geometrically natural. All right. Okay. And I am going to show you how to prove this formula. It's actually not that hard of a formula to prove. By the way, that angle is the angle between the two vectors. Here's the two vectors. Theta is that angle in between them. And let's recognize that angle, I mean, if the one vector is like that, the other vector is like that, right? I'm not talking about the angle as measured horizontally or the angle as measured vertically or the sum of those two. I'm talking about the tilted angle, in other words, like this. Right? So it's kind of a hard thing to get your hands on. But nevertheless, that's the angle between the two vectors. So here's how we prove this result. Look at this modification of the picture. There's the vectors v and w. Notice that I've added to the picture the vector v minus w. Remember how vector subtraction works? That's the thing that when you add it to w, gives you v. Okay. And that gives us then a triangle. And I'm going to cite a fact from high school geometry that I think everyone here has heard of and seen and forgotten. Practically everyone has seen and forgotten the law of cosines. Am I right? Okay, right. So the law of cosines is really handy in a small number of. I mean, it comes up not terribly often, but when it does, it's super convenient to have it on hand. So here it is. This is the law of cosines as it applies to this triangle. Remember, the rough idea is that we're looking at a triangle with an angle that is maybe not a right angle. If that were a right angle, then we would have a Pythagorean formula. And notice the law of cosine starts off looking pretty Pythagorean. Right? So you can think of the law of cosines as kind of a correction term to the Pythagorean formula in the case of a non-right triangle. So this angle here not being a right angle gives rise to, here, why don't I make a better color choice. That angle not being a right angle gives rise to this correction term there to the otherwise Pythagorean formula. Okay, so anyway, there it is. Now I'm going to pull another fast one. This is another trick that gets used a lot in math, which is there's certain kinds of tricks that get used over and over in math, and the more you see them, the more you're sort of unimpressed by them. But nevertheless, it's good to identify these things so you know what your options are. When you're at this stage. So very often in this course, it's useful to compute something two different ways. If you compute this thing two different ways, on the one hand, this thing is equal to that. On the other hand, this thing is equal to that. What that means is that your two results are equal to each other. Right? So you can get information about things that you might actually care about by computing something that you don't actually have to care about at all. Right? And in this case, it's this magnitude squared right there. Magnitude of v minus w quantity squared. I don't actually care about that. But by computing it two different ways, I'm going to get a result that I do care about. So our first computation of that, law of cosines. Our second computation of the same thing, magnitude of v minus w quantity squared. Let me remind you, we just got through talking about how, well, that, magnitude squared means dot product of a vector with itself. And that was the first observation we made about dot product. And we have properties of the dot product. Properties of the dot product allow us to kind of, if you will, foil this out and get this. Right, so here's what we've got. On the one hand, this is equal to that. On the other hand, the exact same thing is equal to that. I don't really care about that thing. As it turns out, what I care about is the fact that these two things are equal to each other. And if you kind of, you take a close look at these two expressions, well, the magnitude of v squared cancels, and the, magnitude of w squared cancels, and then there's a common factor of -2 that you can cancel, and you're left with exactly the formula we wanted to prove. V dot w is magnitude times cosine theta. We win. Okay. All right. I am going to leave it as an exercise for y'all to use this to prove the Cauchy-Schwarz inequality. This is a little bit of an algebraic, I don't want to say challenge, but you got to think about exactly how to set this up. That this fact that we just proved implies that fact that we didn't prove. Right? We never proved Cauchy-Schwarz. I just asserted Cauchy-Schwarz. So I want to encourage you to take a try at this. What I want to suggest that you start with is, don't start with exactly this formula. Start with the equation absolute value of cosine theta is less than or equal to 1. If you write down that equation, absolute value of cosine theta is less than or equal to 1, and then manipulate it, then this will allow you to conclude that. Okay. So give that a try. And again, if you get stuck, office hours, help room, whatever, yeah.
Absolute value of cosine theta is what?
Less than or equal to 1. Yeah. Which I hope everybody remembers. Right? Basic factor trig. Okay. All right. Okay. Yeah. This formula we just proved, you can solve for theta in that formula, and you get this. So what we have here is an observation that the dot product is a handy way to compute this mysterious angle between two vectors. If you have some vector v and w, how would you compute the angle between it? Remember, the angle could be a tilted angle, right? It's not necessarily going to be just kind of a this sort of a thing or a that sort of a thing. It's it's off at some weird angle. How do you turn your head just so you can compute that? Well, you don't need to draw pictures and do heroic geometry. Dot products are easy to compute. Multiply and add. 3-function arithmetic. Magnitudes, not that hard to compute. Okay, there's a square root, but it's doable, right? And arc cosine. Well, your calculator has an arc cosine button. So if you need to know that angle, there you go. That's the formula for how to compute it. All right, quick example. Let's see here. If you want to calculate the angle between these two vectors there, you compute the dot product, you compute the magnitudes, plug into the formula on the previous page. There's your angle. A quick convention that I want to talk about is, notice that I've left this as arc cosine of 4 over 21. I did not utilize the arc cosine button on my calculator because this is an exact answer. Arc cosine of 4 over 21 is exactly what that angle is. If I were to have put that into the calculator and gotten, I don't know, 76.43821557, my calculator only carries so many digits. After that, it kind of rounds off and just says, let's forget about the rest of it, right? And if you just write down just what the calculator tells you, then you were close, but not exactly right. Right? So mathematicians like to leave it in the exact form. There's a lot of information conveyed in the exact form. If you just write 79.64283557, that's some random number. So please leave it in the exact form. I will recognize that if you are actually building a bridge, then you need numbers, right? Because your ruler, your protractor does not have a mark for arc cosine of 4 over 21, of course, right? So that's all. You got to have numbers when it really comes time to cut the wood. Right? We're not going to be cutting any wood in this class, right? In your engineering classes or what have you, if you need to know the numerical answer, go ahead. But in this class, we want exact answers. Okay. So please, no decimal approximations. All righty. So there's neat corollary. That is, if you have two non-zero vectors v and w, then they're perpendicular if and only if the dot product is 0. We're going to use this fact a lot. This is really interesting. Let me emphasize why. Perpendicularity is really geometrically natural concept, right? Right angles. Very cool. You can do a lot of interesting things with right angles. So that's geometrically natural. And that's really easy to compute. And so this is an awesome shortcut. Simple computation, natural and powerful geometric conclusion. So this is another one of those sort of, you need to have this at your fingertips. Make sure, this is what I like to call a sort of a knee-jerk. You should have a knee-jerk reaction that if you ever, in the future, find yourself taking a dot product of two vectors that are non-zero, and if it comes out to be 0, I want you to instantly think in a knee-jerk sense, oh, hey, that means they're perpendicular. Right? Okay. And vice versa. If you know that two vectors are perpendicular, you should instantly relate that to, okay, well that means, of course, that the dot product is 0. Hey, what can I do with that? All right, now there is a shortcoming to this statement, and that is it's not quite true to say perpendicular if and only if dot product is 0. That would be awfully succinct, but there is this little disclaimer over here of, the vectors might be, what if the vectors were 0? The 0 vector dot anything, you're going to get 0. Right? 0, 0, 0 dot, I don't care what, multiply, add 0. Okay. So you got to stipulate that these are non-zero vectors. Because if you think about it, dot product is 0. Does that mean that the vectors are perpendicular? Well, if one of the vectors doesn't have any, if the magnitude is 0, is the 0 vector actually perpendicular? Does that make a right angle? No, it doesn't make any angle at all. Right? It's not long enough, doesn't have enough length to actually even make an angle. It's just, you get into this preposterous world of, if the 0 vector is perpendicular to everything, it just doesn't make any sense. You know what I mean? So this theorem, as stated, is a little clunky, and there's a refinement of this is to come up with a new term, that is the term orthogonal. The term orthogonal most of the time means perpendicular. Most of the time. But to be precise, two vectors are orthogonal if either they're perpendicular or at least one of the vectors is 0. Or said differently, two vectors are orthogonal if and only if the dot product is 0. So it turns out that, so now keep in mind we've just defined this new idea, orthogonality. Orthogonal does not mean quite exactly the same thing as perpendicular. Perpendicular is more geometrically relatable. This notion of orthogonality seems a little bit of a kind of a manufactured, arbitrary sort of thing. It's going to turn out, and we'll see this tomorrow, Thursday I guess it is. It's going to turn out that very often orthogonality is actually more interesting than perpendicularity. When they're different, very often it's the orthogonality you actually care about. So we're going to see this play out, and I have to leave that to when we get there. But anyway, it's a very important concept, and make sure to be aware of the difference between perpendicularity and orthogonality. Okay. All right, a couple of applications of dot products. The first one is components, and here's the picture. If you have a vector W, if you have a vector W, that vector W has a direction, and I'm just going to draw the line. That's sort of a continuation there, W. And if you have a vector V, you might want to know not how long is V, but to what extent does V point in the direction that I actually care about. Let's suppose I actually care about the W direction. That's whatever my context is. I care about how far something points in the W direction, and V points, somewhat in the W direction, but also kind of off in this other direction. So the question is, how can we get our hands on the idea of the extent to which V points in the W direction, and let's ignore how much V points sort of perpendicular to the W direction. Maybe we're playing football, right? Maybe W is the direction. That's upfield. That's the direction where the yard lines are based on going that direction. If you throw the ball, do a lateral 20 yards, but it's completely lateral, and he gets crushed. You didn't get a 20-yard. That's not a 20-yard pass. Right? You only care about the extent to which the pass was going in the direction that you're going. Right? Okay. All right. So it's a little bit of a trig problem. Of course, you can look at this picture if you're interested in that distance. If you know that angle, then you can write down very easily that the component of V in the W direction is, well, take the magnitude of V and then multiply by the cosine of the angle. That's the basic trig. So make sure to look at this as it relates to that picture, and make sure that you remember enough about your trig that this is the right formula. Okay, now what does this have to do with dot products? Well, we're going to take this expression here, magnitude of V cosine theta, and we're going to notice that, well, my gosh, that looks an awful lot like dot product. Dot product is magnitude of V times the magnitude of W times cosine theta. This is really close to that. So we argue as follows then. Here's the formula that we just wrote down above. At least it is after you scratch off magnitude of W there. This is equivalent, morally equivalent. I've multiplied and divided by the same thing, magnitude of W. And then the numerator is exactly the dot product. And as a result, I then have a new formula for how to compute components. And it doesn't even have any trig in it. And that's the point here, right? That's why we call this an application of dot products. I can compute a component that, based on the picture you would think should involve trig, but it doesn't. The dot product has kind of embedded inside of it all the trig that goes into computing that component. So, handy fact. Here's another application. Work. Some of you all may have had a high school physics class. If you haven't, no sweat. So let me tell you what they'll tell you in a high school physics class about work. They'll tell you work is equal to force times distance. Here's the formula. The motivation for this, work is supposed to it's a measurement of how much energy it takes to accomplish a task. So, if I take this thermos, somebody left here. It's weird. This thermos has got some heft to it. There's water in it, right? If I were to ask how much work does it take to lift this thermos up to that height? Oh, wow. Ooh, weightlifting, right? I mean, that's heavy. I mean, there certainly takes a certain amount of effort, a certain amount of energy to accomplish that. I burned like a half a calorie, right? in lifting that up to there. How do you compute how much energy it took to lift this up? Well, the more weight, the more force I'm having to exert, the heavier this thing is, the more energy it takes. Right? The higher I'm lifting, if I lift it way up there, that takes more energy than lifting it 3 inches. Right? So distance matters, force matters, and so the idea is we come up with this formula, and there's much more to say about the physics that we don't have time for, but. Anyway, this is the basic formula for work. Now, there is a dramatic shortcoming in this formula, though. And that is, it doesn't address directions, right? So, if I want to move this thing, there's a certain amount of force that I'm exerting here just in holding this thing up. If I move it sideways, right? That's not work. Now, you could argue that, I'm probably still burning calories, but that's just because I'm being inefficient. If I was smart, what I would do is I would put this on this roller cart and just kind of slide the roller cart, right? And then I would be accomplishing the same task, and I wouldn't be burning any calories at all. One could argue whether that's smart or not. But anyway, it is certainly going to take a lot less energy to do it that way. So when we say work is force times distance, what we mean is force in the direction of the displacement. I don't really care if if the displacement's that way. I don't care how hard you're pushing that way. You're just being inefficient, right? Energy is related to how hard do you have to push in the direction that you're actually going. So if we want to represent the force as a vector, which, by the way, if you think about it, it is. Forces have directions and magnitudes. That's a vector. If we want to represent the displacement as a vector, which again, of course, it is. It has a direction and a magnitude. Okay. Then here's how we really ought to write it down. I've got work is equal to force times distance. The force that I actually care about is just the component of the force in the direction I'm going. Right? I don't care about. Let me draw the picture here. We've got a force F like that, but if my displacement is like that, right? It's only that distance, the component of the force in the displacement direction is all I'm actually interested in. That's what the force should be. And of course, we have a handy dandy formula for components that we just talked about. There's our formula for components. So if you take this and plug that into work equals force times distance, right? The force is that. The distance Well, distance is the magnitude of the displacement vector. So we're multiplying blue times red. Magnitude of displacement cancels, and we get, very conveniently, let's see, color choice, here we go. Force dot displacement. So again, dot product does a lot of this work for it. Oh, gosh, tragic. A lot of the calculation for us, right? The dot product will account for the angle automatically. Said differently, the extent to which work is computed based on, but just the part that's in the certain direction, and thinking about the trig of how you would otherwise compute that component, that's all automatically factored in by the dot product. So this is really a much more natural way to think about work in relation to force and distance. Force and displacement. They don't show you this in a high school physics class, of course, because you haven't seen a dot product in a high school physics class. Right? But this is ultimately much more natural. We're going to make big use of this when we get into Chapter 6. Not today, but definitely want to make sure to remember that work is force dot displacement. Okay, another section down. I do want to start off into the last section here. Correction, the last section that I had any hopes of making progress on today. So the other kind of product, right? We just got through talking about dot products. Remember, there are two of them. The other one is the cross product. The cross product is a bigger conversation. There's weirder connections. The geometry of the cross product is a little bit more substantial. So it's going to take a little bit more doing. It turns out that cross products are closely related to determinants. I think most students here have seen at least something about determinants. I feel sure that every student here will see something in this class that they did not already know about determinants. And while I'm here, let me just go ahead and point out that what we're going to see about determinants in this class is the tip of the iceberg. There's an enormous amount to say about determinants. In Math 216, we're going to spend about 3 days just talking about determinants. It's a lot to say. But anyway, here in Math 212, we'll just do about just a little bit here and there. But anyway, these two things are closely related. So I'm going to present these ideas. Every book does this a little bit differently. I've made some choices here to do this in an order that I think is the most satisfying. It's not the most rigorous. There are a couple of facts that I'm going to just assert sans proof. You're not going to prove them yourselves either. I'm just going to assert that these are true, and we're going to accept that and move on. So that's mathematically, from a rigor point of view, suboptimal. But you commit that one sin, and everything else kind of falls into place in a really beautiful way. So I think this is geometrically more satisfying. I want to start off with a third concept, which is the concept of right-hand order. So it turns out all three of these ideas are related to each other in a really important way: cross-product, determinant, and right-hand order. I like to segue into the concept of right-hand order by talking about a two-dimensional version of it, and that is clockwise versus counterclockwise. So here's what I'm talking about. Suppose I have two vectors, v and w, and I want to make a list. So in other words, not just v and w, no particular order. I want to write down an ordered list. I want to think of one of these as being first, and I want to think of one of these as being second. And with the understanding that one of them is first and one of them is second, so I could write v comma w, for example, or same two vectors. I could write w comma v. Looking at these two possible ordered lists, how would I distinguish these lists from each other? Now, the silly choice would be to say, well, this is alphabetical order, and this is reverse alphabetical order. Right? Well, that's got nothing to do with geometry. There's no sort of natural meaning there. Okay, so in a way that's geometrically natural, what would I say? And the answer is we're gonna develop the following rule, and that is to say, well, look, whichever vector is we're going to talk about this one here, by the way, v comma w. Whichever one is first I'm going to then ask the question, which direction would I have to rotate to get to the one that's second? And counterclockwise. All right, so I would call this a counterclockwise list. Yeah? Fair enough? So, why do we care about this? I'm going to have to leave that until Thursday. But W, V is a counterclockwise list because of this picture, and I leave it as an exercise for you guys to confirm that, as drawn, W, V would be a clockwise list. Okay, so something to chew on, but as you're hopefully having some cookout for 4th of July or whatever it is that you want to do, is what would be a three-dimensional version of this concept? The idea of clockwise versus counterclockwise. Is there a three-dimensional version of that? Suppose you have 3 vectors in R3 instead of 2 vectors in R2. Is there a kind of equivalent idea? And it turns out that there is, and we'll talk about that on Thursday. Y'all have a great 4th of July. See you later.